Thank you for all for showing up, and it's great to see so many faces. Thank you. I want to talk about some work with Jason Gaitonda. Jason is a graduate student at Cornell and is on the call and is manning the Q&A button. So if you have questions that you want to interrupt me with, that's fine too, or questions that you think Jason can answer, just put it in the Q&A box. And Jason, if you think I should explain this out loud, then please speak up. With that, I want to talk about a paper on stability and learning in a strategic queuing system. And before I tell you exactly what is the model and what exactly we are doing, let me give you a little bit of background on what is the bigger question that we were interested in trying to address. So I've been interested in, I've been interested in studying repeated games or repeated strategic interactions for quite a while now. And I guess maybe my favorite examples for repeated interactions or repeated games are traffic routing, where I guess the game was that every morning you get in the car and you commute to work, and you might, unfortunately for you, might be facing some traffic jams, maybe not quite as bad as what the picture shows. And again, this is a congestion game. The model is that as there are more cars on the road, you're going to take longer to get to work, and you would like to get to work as fast as possible. And this is a repeated game in the sense that you interact in this, you participate in this interaction every single day. And I guess what I would like to think about is a version of what happens in a repeated game if the following kind of basic setup. So agents participate in a fixed game. Again, my favorite example is maybe traffic routing, but auctions, and another example, the bidders in an online auction participate in bid over and over again, and that's also is, you know, roughly the same game being repeated over and over again. The player's goal is to selfishly minimize their cost. That is, the assumption is you want to get to your destination as fast as possible. Maybe your average time it takes is what you're minimizing, or the average value you get out of the auction is what you're trying to maximize in the auction case. And here is maybe the most important assumption for this talk. I'm going to make the assumption that every player who participates is running some sort of machine learning algorithm to figure out what might be the good action to take here. So what do I mean? What I mean is that maybe they participate in this auction, maybe they showed up starting to drive in a new city, or maybe the coronavirus hit and the traffic patterns changed. And in the beginning, they do something, they drive on some paths, but they don't know what to do. But as life goes on, or days go on, they experiment, and after a while, they have a better idea of how to play this game. And every day they take the experience they have and use it to figure out what to do the next day. I think it's not controversial that in many, many real-life applications, machine learning is what's happening. But I'm going to assume, because this is a theory talk rather than an experimental talk, that the learning is good enough to satisfy the following very nice condition, which I guess usually goes under the name of no regret condition. And this is what the condition says, that if I take sum over time for some time horizon, capital T, if I sum over time how much cost they accumulated, so sum of all they cost of all the times, and compare it to a fixed strategy with hindsight, that is, there is a particular path, if they only drove on that path every single day, that would be the path X. What cost would they have had? And one will assume that they don't do much worse than any fixed strategy with hindsight. Much worse here is something of the form that this last term, which we usually call regret, is doesn't go linearly with time. It goes less fast than linearly, like root T or something even better. I want to propose that this is a weak condition, and I will have a whole slide sort of trying to convince you or spend a minute repeating the reasons why this might be a reasonable condition. But before I do so, let me point out this is a weak condition. You can easily do better than this. If it turns out that when it rains, you would be better off driving on the highway, but when it doesn't rain, there is some low pass in the back that does better. That's not in the comparator here. I'm just asking you, if the highway is always good, please wake up to this fact and drive on the highway. If the low roads in the back are always good, please wake up and do that. That's what it's asking. So this is not a golden standard that will be hard to reach. Instead, it's a standard which I think is a weak standard. I think people, algorithms, methods can do much better than this, and I hope that they do at least as well. That is, if they do better than this, that's fine with me, as long as they don't do worse. So here is what I'm trying to offer about this learning condition. First of all, the history of thinking about this kind of learning goes back to Hanan for before I was born, and it's often goes under the name of Hanan consistent. There are multiple very, very simple algorithms, and actually maybe regret matching should have been on my list too. There are many super simple algorithms, basically saying that, do what, if something seemed really good in the past, then do that one. I like it as a behavioral assumption, and that's basically what I was trying to argue even before I got to this slide. What it says is that there is a single action or single pass in the ratting case that's really good for you, then please wake up and do at least as well. It's asking you if there's a consistently good solution, your algorithm or your learning method should be good enough to wake up to this fact. If you do better than this, cool. But if you do worse than this, you should feel pretty damn bad. Like somehow there is a really good solution. With hindsight, you realize that there's this solution that's amazing. It will get you very fast to your destination every single day. And yet, apparently you don't notice it. That does sound very, not good for your learning algorithm. And I want to last point out that some of the literature in this repeated game setup is assuming that the players collectively somehow manage to converge to a Nash equilibrium. This is a much weaker assumption than that. If they did converge to Nash equilibrium, then having no regret is literally the definition of the Nash equilibrium. So basically what it's assuming that they satisfy this classical Nash condition without the stability that they have to reach a single solution. They can, the solution can evolve. Also, actually, maybe a last point in defense of this, I can play no regret and reach the condition myself, even if the other players are not rational or smart enough to reach their own condition. This is a condition for a single player rather than a condition on the whole game, like Nash equilibrium. You might have seen me or many others talk about, and that's sort of the main topic of this talk, of trying to think about what happens in games as people play compared to some sort of social welfare. I guess the classical name that this has been dubbed at is called the price of anarchy. And I guess started with Koutsoupias and Papadimitriou, comparing the social cost of Nash equilibrium compared to a centrally designed optimum. There's a whole bunch of literature about this. What we're doing is maybe more analogous to this old result of Tim Rovgarden and myself from the early days of price of anarchy, which is what the CS literature called bi-criteria optimization. What it's asking is, how much extra resources do I have to give you in a network to guarantee that the delays won't be any worse than it would have been in a centrally designed optimum? So what it's basically saying, that if you put the capacities in your network double what it what the centrally designed system would want, then even a Nash equilibrium will have a reasonable cost. Okay, so it's more a sort of actionable question. What extra resources do you have to give a system so as to guarantee that a selfishly achieved solution is no worse than a centrally designed optimum could have been? One beautiful line of work that have been very prominent, and I might have even talked about this or some part of this at one of the previous year's Stony Brook conferences, is a sequence of papers which is trying to basically all say that whatever we proved about Nash equilibrium, if instead all the players participate in no regret learning, we can make the same statements. That is, the same results about price of energy, that is the quality of the overall solution, or the bi-criteria band, all apply. They don't have to find the Nash equilibrium. It's enough if they all participate in some sort of learning. Yeah, this is maybe less interesting in traffic routing because that's a congestion game, and therefore learners will actually find the Nash equilibrium, but very interesting in auction games where learners do not find the Nash equilibrium, but yet overall the social welfare in the system will apparently be high. So this is all the background. And now let me point out the sort of most critical, most important question here that we're trying to address. This set of results, as beautiful as it is and as much as I really like it, even with this handicap, has a very critical assumption. The assumption is that every iteration, you play the same game, but it's a fresh copy. That is, there is no carryover effect between the runs. Well, except that, of course, your history, you learned from the previous run, but there is nothing that changes the game. And I guess, let me ask you, is this a reasonable assumption? And I guess our basic answer is actually no, of course not. So let's go back to traffic routing. And I had two pictures on my slide. One was sort of a morning rush hour kind, and one was a IGO semantic picture of packets on the internet, maybe, or at least that's what I intended it to be. Morning rush hour is quite reasonable, the assumption. No matter how bad traffic was Monday morning, I think by Tuesday morning, they're all gone. You can start all over again. In the middle of the night, the traffic is actually very light everywhere. But it's definitely not reasonable in packet routing. If the internet is congested, then what really happens is a whole bunch of packets got dropped, and then I guess the internet system will try to resend the packets that got dropped with some delay. So if the internet is congested in minute number or second number 17, then second number 18, the very same packets are causing congestion, and definitely it's still congested for the reason that the packets are still there. And this, literally the second one is what we're trying to model in our paper. The higher level question we want to ask, and I will offer this in a very, very simple model only, is what can we say about the quality of competitive or learning outcomes in a repeated game when the game has a carryover effect? And again, the particular carryover effect I'm going to talk about is packets getting dropped and therefore have to get resent. As I try to promise, and maybe the title promised it also, I'm going to promise it we're going to study this in a much, much simpler version than the whole internet getting packets sent, but instead a simple queuing system. And here is our model of a super simple queuing system where the queues will try to learn which server can serve their packets. So in this picture, these blue squares are queues, and the queues will have some packets, and their servers they want to send the packets to. And up front, the queues have no idea both about how good are these servers or which one is the good server, and also have no idea what are the other queues doing who are also trying to get their packet servers. served. So it's both sort of learning, you have to figure out which servers are good, and also a competition, the queues are competing with each other. So very concretely, each queue will have an arrival rate, a Bernoulli process in which every second there is a new, or every timestamp, there is a new packet arriving at qi with some probability lambda I. The server's quality will be simply a probability mu j that server j is succeeding at serving a packet in every single period. And the model will be that in every time, every queue can take one of its packets and send it to one of the servers to try to get service. You know, some of them will succeed and some of them will fail. And I guess, but servers can only process a single packet at a time. So for example, on the top server there are 2 packets coming in. Clearly one of them will not get served. And even possible that possibly neither gets served because the server fails. Remember, there is a uj probability of success here. Every unserved packet goes back to its queue, and the queue can try it again. Like next iteration can say, hey, you know, let me send it again. So this is our simple model of a dropped packet, which needs to get resent. And again, maybe a key assumption, we're assuming that the queues are using a no-regret learning algorithm to try to figure out where the best service is. Okay, so that's our model. If there are questions, you can either speak up or put it in the Q&A box, and hopefully Jason will try to answer. Let me try to give you some special
Can I ask a question?
Sure, go ahead.
Yes. So basically, when the issue of the carryover between one stage to the next is basically an instance or an example of a stochastic game. And the question is, what I understand that here you are applying a method or a system or something to some specific queuing model of a stochastic game. What class of stochastic games would it be applicable when you progress forward?
What a cool question. Thank you. I think this is one of the questions on my closing slide. It would be nice to extend this to many other stochastic games. I'm not sure. I think that's my best answer, but it's a cool question. And definitely, this will turn out to be a stochastic process, and that's how we're going to analyze it as a stochastic process. So definitely good insight on where I'm heading. Before I get there, I want to give you some special cases. So again, the main question we're asking, which I try to say ahead of time, but can't repeat it often enough. I'm hoping that if you upscale the abilities, the servers, if the servers have enough slack, it's a little bit better servers, then despite that you're not coordinating, they're just learning to figure out what to do, they will do okay. I'm going to like the result if it says that, you know, if we add a little bit of extra capacity to the servers, life will be okay when they're coordinating, when they're learning, compared to a central coordination, and won't like it if it says that you know, selfish learning is really disastrous. No matter how much extra capacity you give, they're never going to succeed. So simple example, one queue, one server. This is really easy, no learning, no competition, but maybe good to get the basics straight here. So there's a single arrival rate lambda and a single processing rate mu. And you can think of this as a biased random walk on a half line, where the half line is the number of packets that this queue has in its process, and it's standard from basic random walk is that if lambda is strictly less than mu, then the queue will expect it to say bounded size. If lambda is equal mu, then it's an unbiased random walk and will grow linearly or square root of t as time t. And of course, if lambda is strictly bigger than mu, you're definitely in trouble, and the queues will grow like crazy.
Eva, sorry to interrupt. I think Jorgen has a question. If you'd like to unmute yourself. Okay, it's just for clarification, Eva, what is the hypothesis of the queues about the servers? Do they believe they are do they have a Bayesian view, or what are the views, distributions, or things like that, or how do you think of that?
That's also a great question. At the moment, I'm not making assumption. If they have a Bayesian assumption of how the queues are, that's fine with me. But actually, no regret learning, they can learn what they are, even if they don't actually know. It's like, and maybe the next slide will help you answer this question, and it's worth going there as part of my answer. So my next example is when there's learning but no competition. So a single queue and multiple servers. So what's happening here, I did not make assumption. They don't know which one, how good the servers are. They have no idea. But a simple, this is classically known as a multi-arm bandit problem. And even without assumptions on what they might know about the abilities of the bandits, a simple exploit strategy, just try them and record how good they are. Very fast, they can learn what's really happening. There is a nice paper that actually was served part of my motivation to think about this model. Krishnaswamy, Sen, Johari, and Shakotoi, a couple years ago, I guess by now 4 years ago, has a paper on this system understanding, and what they're asking is how will these queues behave, and the basic result is that like you would expect in learning, it will go this time logarithmic in the lengths of the queues for a while, but after a while this queue will figure out which one is the good server, and then the queue will go down and will actually vanish or essentially go down to nothing. So what we're trying to do is add a competition feature to this. So again, the same model, queues have packets coming in and servers have abilities, but now they're competing with each other. There is some work which I'm going to skip over at the for saving time, in case there is a single learner and we're really doing competitive or cooperative game theory maybe, or cooperative learning. But what I'm interested in is individual learning, as in a game. Every queue separately is trying to learn what's best. If they're competing, I guess I have to first answer the question of what would happen if we coordinated? That is, what's my baseline? How am I comparing it to? So my baseline measure will be, suppose there is a great helpful coordinator who tells every queue where to send their packets. How much capacity on the servers do I need for every packet to get served in a timely manner? And to improve my notation, let me assume that, just for notational simplicity, that both the queues, the arrival rates at the queues and the abilities of the servers are sorted with the lower indexed one having higher arrival and higher ability to serve. Under this assumption, maybe you won't find it surprising that this is a very simple, again, sharp condition, analogous to the condition we had in a single server, single queue. What we need is that for every k, so for example, k equals 1, the top k queues combined should not have more packets than the top k servers. So the top 1 queue cannot get packets faster than the best server. The top 2 queues should not get packets faster than top q servers. This condition is necessary because I did make the assumption, which is true in some packet routing version, that every queue can only send to one server at a time. They can't parallel process and send it to multiple servers. So the k queues that have a lot of packets arriving can only use k servers at any one time. And as a result, if the top k servers don't have enough capacity, this is hopeless. So the necessity of the condition is kind of follows from this pretty obviously, and I guess it's not super hard to prove that this is a sharp, necessary, and sufficient condition. Before I can go to a competition version or go to our results, I have to admit I've been sweeping an important question under the rug. in the competition version, is if a server gets multiple packets, how will they decide which one to serve? And I guess we offer two options that seem the two natural options to us. Option one, uniformly at random. And option two is that we actually timestamped the packets and we'll favor old packets. And our basic results will say that uniformly at random is really bad. Uniformly at random, no matter how much, or almost no matter how much more capacity you have on the server side, it's not going to help. Some queues will back up like crazy. But if you give benefit to the oldest packets, then a factor of 2 is enough. That is, if the system capacitated a factor of 2 up from what's necessary for a coordinated system, then even though they compete and they fight with each other, there is enough capacity there that they're going to, the packet sizes will remain banded. And in fact, this factor of 2 band here is tight. That is, less than this capacity is not enough. So what I'm hoping to do in the remaining some number of minutes I have, maybe 5.
About 5 to 10 minutes.
Exactly, is give you, first of all, a sense of what's wrong with the uniformly random selection, because I think that's very insightful to see what is the system we're dealing with, and then have a little bit of insight of how did we prove this band that's our positive result. So here is our negative statement, that is why uniform selection is bad. Don't look at the exact details of the arrival rates and service rates. Think of C as some sort of large constant. And what I'm trying to do is a matching system of queues and servers. There is one queue with a pretty large arrival rate and one server that's really perfect. It can serve packets with probability 1. And then a bunch of other queues with very small arrival rate and a matching server with a little bit bigger service rate. So we have a slack of C. The capacity of the system is a factor of C up from the arrival rate of the queues. And indeed, if you centrally coordinate, as we know from a single queue, single server system, it's perfect. Every queue should send to this personalized server, and he has a factor of C less arrival rate than the queue, so it will all be okay. But that's not what they're going to do selfishly. What they're going to do selfishly is this. There is a really good server there. And in fact, even if as many as n of them compete for the very good server, they get a service rate of 1 in n, which is better than the service rate of the C cubed over n. They would, they can get a service rate much better than the C cubed over n, and they will compete, which is really cool for almost all queues, except the big queue will back up like crazy. So maybe that's sort of, they're all getting better service, except for this one queue, the first queue, which has a high arrival rate, and that one's backing up. So we're claiming that if you timestamp the packets, then this is not going to happen. So this is our main theorem again. Again, it says that it's supposed they're timestamped. Everyone does learning, and queues serve the oldest, attempt to serve the oldest packet. Then a factor of 2 capacity is enough, and then this factor of 2 is tight. So I definitely won't show this to you. So let me give you a little bit of an idea of what goes into the proof. As we got the hint already from the question, this is a stochastic, nice stochastic system, and that's how it's going to get analyzed. We're going to use a potential function, and one claim that this potential function will stay reasonably bounded, and that will show the result. So here is my favorite potential function. I guess it's built out of little potential function. For every time tau, I will have a part of the potential phi tau, which is the number of tau or older packets in the system. So super old packets contribute to this potential function a lot of times, right? It's older than 10 days old, it's older than 11 days old. Phi tau counts how many packets are there that at least tau days old, and I add it up over all taus. That's my potential function. Our main mathematical tool is this very nice and useful theorem of Pimentel and Rosenthal that says that a random process that's sufficiently regular, and I'll come back to what sufficiently regular means here, and has whenever phi is large, it should have a negative drift, is guaranteed to stay bounded in expectation. So what I need to prove, basically, there's a technical condition that it should be sufficiently regular. Again, I'll come back to this. But the main essence is, I want to claim that when phi is really big, or any big, then there's negative drift. That is, there are many old packets around, phi is high, then this function phi is expected to come down. And this is what I have to prove using the fact that they all no-regret learners. So why is this phi as a good function? Here is sort of the main idea of the proof. I'm looking at a particular time tau and say, look at all the tau or older packets. Because we gave old packets priority, this group of packets as a group has priority over every other packet. You know, between them, I don't know, but as a group, they have priority. So one of two things will happen. If I look at a time window, either the best servers will get a lot of tau queues sending them packets, and then in expectation, a lot of them will get served because they have priority. One of them will get served always. Or they don't send enough, but they would have had priority, which means they should regret not doing it. There is a single server out there would have been really good for them. No regret condition guarantees that, well, maybe they're not sending here, but they're doing at least as well had they sent it, and therefore they're actually doing quite well also. And this is exactly what's giving us the band. I said this for a particular time tau, but of course I don't know what's the right tau is. So what I have to do is simultaneously apply this band for all taus. Hence my potential function sums over all possible timescales to prove the negative drift. For some technical details, and this is really getting swept under the rug here, I guess what I needed is actually something a bit stronger for the no regret condition. I want that the no regret happens with high probability. This is because it's a queuing system. Super bad situation will arise, virtually certainly, and I need to be able to recover from them. I want to make that no matter how long you run it, nothing will go wrong, or not for long times. The technical condition in the Pimentel-Rosenthal theorem is that we need this process to have bounded moments, and to guarantee that our process does have bounded moments, I actually slightly cheated you, and the potential function we're using is not the number of packets, but instead a function of the age of the oldest packet. Turns out that this allows us to use a deferred decision switch to how the probabilities are worked at, and that works better. But in the spirit, we are using the number of oldest packets. And if I want to use the age, then here is an expression I wrote up here of how the age roughly relates to the number of packets, and that's actually what we're using. And I'm going to stop here and maybe tell you something that I also was already foreshadowed by the question. So I think I have been working on learning in games for, I don't know, probably last 10 years for sure. And I really like this area, but not much known in games in carryover effects. And I guess that is definitely a very important open area. We proved something in a super simple model with packets and packet priorities. It would be very nice to extend it to many other applications. I guess from an application perspective, the killer application would be here, auctions with budgets, where the carryover effect is, if you won the auction, you have less money left. That's just how life works. And that's also a similar carryover effect, but at the moment, we don't know if that works, and I don't know Abraham's question of what other systems it extends to. And generally, somehow we switch to a different outcome feature, it's not as much social welfare. It's like, what does it take? How much capacity does it take to generate stability? There are other quantitative measures of this form that would be nice to look at. And I'm going to thank everyone for the attention and stop here.
Thank you, Eva, so much. Yes, we cannot applaud. I mean, it's a bit inconvenient here on Zoom, but that was a great talk, so thanks a lot. Let me see if there are any questions, if speakers, if participants with audio video interaction, if you want to ask a question, you can raise your hand. And also, I see that we have some questions in the Q&A that have been answered by Jason. So if you don't have any other questions, Jason, is there anything you would like to share with us from the questions you've been very quickly and thoroughly answering in the Q&A text box?
Yeah, I mean, I don't think there's too much to say. There was a couple nice questions, but I think they were mostly like clarifications. So,
all right, good. Anything you want to say? I know there was a question at the beginning, a bit like a broader question about machine learning.
Yeah, right. Okay, so I guess there was one question on do you see in the coming future the extensive use of machine learning models in the domain of game theory, and will there be an algorithm that can do the tedious game theory calculations to reach the desired outcome? So I mean, I wrote an answer in there, something quick, but so I guess the first question is the extensive use of machine learning models in the domain of game theory. I mean, that's certainly something that we're very interested in doing. In practice, I think people are tending to use these things as opposed to reasoning very deeply about, you know, various forms of Nash equilibria. So we're very interested in kind of understanding, you know, what we can still say about these sorts of outcomes. And on the second question, I don't know if I understood it correctly, but I think the answer is generally no, just in the sense that there's lots of these seminal results from CS in the last 10, 15 years, basically saying that even in very, very simple like 2-player games, 3-player games, whatever, it's actually like provably hard to compute Nash equilibria. So, I mean, given this, it seems like, if I'm understanding the question correctly, I'm going to say no on that. And I think that was basically it. Then there was another question about the baseline case.
So actually, just to extend the Jason question, there is some amount of evidence, at least in adductions from Microsoft or Google, that systems do become pretty damn stable, which is an evidence that whatever they were doing, which I think is actually machine learning, they somehow managing to find the Nash equilibrium despite the hardness results out there. So there are hardness results that says that in the worst case, finding equilibrium in these auctions is hard. And then there is practical evidence that says machine learning, which is definitely algorithmic and pretty simplistic, apparently seem to find it. So I think what is missing, in my mind at least, is a theoretical explanation of what's special in the auction kind of things that are actually happening. What property do these auctions satisfy to avoid the worst case of the computational difficulty? It would be like, I do understand both sides of the coin, and there must be something, and hopefully something that we can quantify as a theoretical statement, that the practical games, that the auction games that are happening are somehow simpler or different and not general, so that the hardness does not apply to them. I would love to have a theorem of this form.
Eva, it's rather than looking at the worst case, do computer science people look at the average case in their definition of how performance?
Yeah, they do, or at least increasingly more people do. Of course, the question is, what's the average case?
Yes.
So what are you averaging over? My favorite version of the average case personally, and you can tell me that that's not your favorite version, is something that goes under the word of smoothed analysis. That is, you can give me a worst case version of everyone's value is some, your value for this auction is 10 cents and mine is 8 cents. And then I put a little bit of a Gaussian noise in the values, because you didn't really mean 10 cents, roughly. And I didn't mean 8 cents, I meant it roughly. So I changed everything with a bit of Gaussian noise. And then the question is, does an averaging over this Gaussian noise? I think this is better than when you make things of the form of everything is uniform random. And to give you a sense of where I'm coming from, this all started with linear programming, and it's very successful in the linear programming domain, where they say that, you know, AX less than B, the B's were a bit random, Gaussian noise on the B's. As opposed to AB, everything is random, in which case I know how to solve linear programs. Oh, there is no solution. Random AX less than a B, the polytope is empty, I know that, don't worry. That's a pretty dumb answer. That's not what we meant. Yeah. But the Gaussian noise on the B's, I think that's very reasonable. It's a little bit odd, like we didn't mean it exactly. And in linear programming, it worked. That is, a Gaussian noise on the B's is enough to make some versions of the simplex algorithm efficient. In many of the hardness results, unfortunately, it's not working. Gaussian noise of this little bit is not enough. It still remains hard.
Thank you.
All right, thank you so much. And we are going to now